Okay, so first things first, we've got lots of letters on this particular page here, and most of them you don't necessarily need to be able to remember what the symbols mean. In a physics exam, if you need to know, for example, what Ra stands for, you will be told in the question that Ra is radium. So you don't actually need to remember many of these at all. The only ones that you do need to remember are He and E. He is a helium nucleus, and that always has the numbers 4 and 2. So 2 is the number of protons, so there's 2 protons, and 4 is the number of nucleons. So there's 2 protons, and then that must mean there's 2 neutrons as well. So 4 is the number of nucleons, 2 is the number of protons. This is an alpha particle. So an alpha particle also has the same numbers associated with it. And we can use these two symbols interchangeably. In exams, it's usually He, but they might sneak in the alpha symbol. Similarly, for the E, that is an electron, and electrons have the numbers 0 and -1. If you're not sure where that comes from, don't worry about it when you're doing nuclear equations. However, you do need to sort of understand that for other parts of questions, and that's in other lessons. The electron, in this case, is a beta particle. That's the symbol for a beta particle, and that also has 0 and -1. And again, these two symbols are used interchangeably in GCSE. Okay. When it comes to the actual equations, so let's have a look at this top one first. 232 and 90, thorium. And then we have an arrow, which means there's a reaction that happens, and it becomes a helium nucleus, which we just talked about, an alpha particle, plus radium. And we're missing some numbers here from radium. And that's basically what this question is asking us to do, is to fill in these two numbers that go there and there. To do this, we can actually separate this into two parts. The 90 and the 2 we can kind of ignore for now. We're just interested in the 232, the 4, and the number that goes at the top just here. And what we end up doing is we end up saying that the numbers on the left-hand side of the arrow, in this case 232, have to equal the numbers on the right-hand side of the arrow. So in this case 4 plus whatever we put just here. So we can actually work out what goes just here by doing a simple bit of maths. I'll rub those out so I've got a bit of space. And what we're going to do is we're going to do 232 equals 4 plus a number that we don't know. Okay, we can rearrange that quite simply. To get the number that we don't know, we're going to do 232 minus 4, which equals 228. That's the number we put here, 228. So in this case, 228 plus 4 equals 232. And that's as simple as it is. The bottom numbers, 90 and 2, well, the same rule applies. Whatever we want to put here, at the bottom number of radium is going to be the number of protons in radium. And if we add the number of protons in radium to the number of protons in an alpha particle, we must get the number of protons that were in the original thorium atom. So the number that goes here, plus 2, has to equal 90. So if we rearrange that, what we end up with, just get rid of all this, write it again properly, so it's 228. We have 90 minus 2, which equals 88. We've got 88 protons. And basically what this is the conservation of mass. What that means is the number of protons before has to equal the number of protons after, and the number of nucleons before, so protons and neutrons, has to equal the number of nucleons after. So we can always find these by simple addition. Right. Gets a little bit harder when we're looking at a beta particle, because we've got this -1, so we've got to think about adding negative numbers. But it's the same idea. We look at the numbers on the top, and we've got 14 on this side, Well, 0 and whatever number goes just here must equal 14. So 14 minus 0, well, that's 14. Turns out the number of nucleons in beta decay doesn't actually change. A little bit more tricky on the bottom. We've got 6 has to be the same as minus 1 plus whatever goes underneath the 14. Okay, so we're going to do 6 minus minus 1. So when we do minus minus 1, that's the same as plus 1. 6 minus minus 1 equals 6 plus 1, which equals 7. So we're going to put 7 just here. And again, you can see if we count the number of protons and the number of nucleons, they'll be the same either side of the arrow. So if we look at the top, 14 is the same as 0 plus 14, and 6 is the same as minus 1 plus 7. So on both sides, we've got the same number of nucleons, the same number of protons. Next one, we're actually missing, the next two, we're actually missing the type of radiation that has been emitted. Now, I think these are actually slightly easier. We've basically got two options. We can either have this or we can have this. So here we've either got a 4 and a 2, or we've got a 0 and a minus 1. Well, let's have a quick look. 216 and 212, well, they're 4 different. So I'm leaning towards this being the answer. Let's just double check it though. We've got 84 and 82. Well, they're 2 different. So they're two numbers apart, so it is. So we can rub that out and we end up with this. So this equation here was missing an alpha particle. Similarly, for the next one, we've got 241.94 and 241.95. Well, that looks very, very, very much like we're going to be having a beta particle, because this number and this number are the same, and this number are 1 different. So let's put that in and see if it balances. Put 0 minus 1. Oh, it's a smiley face. And an electron. We can see that this does balance now. So 241 equals 0 plus 241, and 94 equals minus 1 plus 95. The last question, we're given the products. We need to work out what the numbers here are. So for the reactants, and this one also relatively straightforward. The numbers here, 221 and 4, has to equal what's on the other side. So 221 plus 4 is going to be 225. And then on the bottom, 87 plus 2 equals 89. And there we have it. Simple addition all the way down. They look a little bit intimidating, but in actual fact, it's all just addition and subtraction. And the only real hassle that you've got is a negative number in there. So you can be adding or taking away a negative number, which can throw a little bit of a spanner in the works, but generally speaking, not too bad. Anyway, hope that helped.